Imagine looking out into the vast, dark expanse of the universe, a sea of near-infinite blackness dotted with countless stars and galaxies. Now, picture a lighthouse in this cosmic ocean, a beacon so intensely bright that it outshines entire galaxies, visible even from billions of light-years away. This, my friends, is a quasar. These objects are not stars, but the furiously active hearts of distant galaxies. At their center lies a supermassive black hole, a gravitational monster millions, or even billions of times, the mass of our sun. As this black hole greedily pulls in surrounding gas and dust, the material doesn't just fall in quietly. Instead, it forms a swirling, superheated disk of matter called an accretion disk, which glows with unimaginable brilliance. This process of feeding is what makes a quasar one of the most luminous objects known to humanity. The friction and gravitational forces within the accretion disk heat the material to millions of degrees, causing it to radiate energy across the entire electromagnetic spectrum, from radio waves to X-rays. One such cosmic lighthouse is a quasar named RxJ1131. It is located a staggering 6 billion light-years from us, meaning the light we see from it today began its journey when our solar system was just forming. Studying objects like RxJ1131 is like having a time machine. It offers us a precious glimpse into the universe's distant past, showing us what galaxies were like in their energetic youth. The sheer distance to these quasars makes them incredibly challenging to study in detail. From our vantage point on Earth, even a colossal object like RxJ1131 appears as just a single, tiny point of light. Trying to see the structures immediately surrounding its central black hole is akin to trying to spot a grain of sand on the surface of the moon with your naked eye. It's a task that seems utterly impossible with our current technology. Yet, astronomers are a clever lot. They have found a way to use the universe itself as a giant magnifying glass, allowing them to probe these enigmatic regions and uncover secrets hidden for billions of years. This quest to understand quasars is fundamental to our understanding of the cosmos. These objects play a crucial role in the evolution of galaxies. The immense energy they blast out into space can influence star formation, sometimes triggering it, and at other times blowing away the gas needed for new stars to be born. By studying quasars like RxJ1131, we are not just looking at a bright light in the sky. We are piecing together the grand story of how galaxies, including our own Milky Way, grew and changed over cosmic time. It's a detective story of the grandest scale imaginable, written in the ancient light of the universe. Now, let's venture closer to the heart of the quasar, to the very edge of the supermassive black hole itself. Just outside the event horizon, the point of no return, lies a region of extreme physics known as the corona. This isn't like the gentle, wispy corona of our sun that we see during an eclipse. A black hole's corona is a far more violent and mysterious place. It is an incredibly hot, tenuous cloud of high-energy particles, a sort of ethereal halo of plasma where temperatures soar to millions of degrees. This superheated gas is what makes the region glow intensely, particularly in high-energy X-rays, making it one of the brightest sources of X-rays in the universe. The existence of this corona is one of the great puzzles in modern astrophysics. We know it's there because we can detect the X-rays it emits, but we don't fully understand how it forms or how it gets so mind-bogglingly hot. One leading theory suggests that powerful magnetic fields, tangled up like a chaotic ball of cosmic string, get twisted and churned by the black hole's immense gravity and the swirling accretion disk. This process could accelerate particles to near the speed of light, heating them to the extreme temperatures we observe. Understanding the corona is therefore crucial, as it holds the key to comprehending the physics at play in the most extreme gravitational environments in the cosmos. Think of the black hole system as an engine. The accretion disk is the fuel tank, providing the raw material. The black hole is the engine's core. But the corona is like the ignition system, the spark that generates the most energetic output. It's the source of the high-energy radiation that interacts with the accretion disk and can be launched outwards in powerful jets. Without a proper understanding of the corona's size, shape, and energy source, our models of how black holes influence their host galaxies are incomplete. It's a missing piece of a very grand puzzle, and finding it would be a monumental step forward. For a long time, directly measuring the size of a black hole's corona was considered impossible. It is simply too small and too far away to be resolved by any single telescope on Earth. Astronomers knew it had to be a relatively compact region, nestled deep within the quasar's bright core, but its exact dimensions remain purely theoretical. Was it a vast, spread-out cloud, or a tiny, concentrated sphere of energy? Answering this question would help scientists distinguish between different models of black hole physics, telling us whether the corona is shaped by magnetic fields, the base of a powerful jet, or something else entirely. The challenge was clear. How do you measure something that is, for all practical purposes, invisible? To solve the impossible problem of seeing the unseeable, astronomers turned to a remarkable phenomenon predicted by Albert Einstein's theory of general relativity: gravitational lensing. Einstein showed that massive objects, like galaxies or clusters of galaxies, warp the very fabric of space-time around them. Light, which normally travels in a straight line, is forced to follow these curves. This means a massive object situated between us and a distant light source can act like a giant cosmic lens, bending and magnifying the light from the background object. Its nature providing us with a telescope far more powerful than anything we could ever build ourselves. In the case of quasar RxJ1131, fortune smiled upon us. By a wonderful cosmic coincidence, a massive galaxy lies directly in the line of sight between Earth and the quasar. This foreground galaxy acts as a powerful gravitational lens. As the light from RxJ1131 travels towards us, it is bent around the galaxy, creating not one, but 4 distinct magnified images of the same quasar. It's like looking at a single candle through the distorted base of a wine glass and seeing multiple flickering flames. This lensing effect already gives us a brighter, more detailed view than we could ever get otherwise. But it's only the first part of the trick. The real genius of this observation comes from an even finer effect called microlensing. The foreground lensing galaxy isn't just a smooth distribution of mass, it's filled with billions of individual stars. Each of these stars has its own tiny gravitational field, and as they drift through the galaxy, they pass in front of the light paths of the lensed quasar images. These individual stars act as small, moving magnifying glasses, causing the brightness of each of the 4 quasar images to flicker and fluctuate independently of one another. It's a subtle dance of light, where different parts of the quasar's core are magnified at different times. This flickering is the key. By closely monitoring the changes in brightness of the 4 images, astronomers can deduce information about the structure of the light source itself. For instance, if the source is very large, the microlensing effect from a single star will be subtle, as it only magnifies a small portion at a time. However, if the source is very small and compact, the star's passage can cause a dramatic spike in brightness. By analyzing the statistical patterns of this flickering across all 4 images, scientists can reverse engineer the size and structure of the region emitting the light, in this case, the mysterious corona of the black hole. Using this brilliant combination of gravitational lensing and microlensing, astronomers, led by a team from Leiden University, analyzed data from the Atacama Large Millimeter Submillimeter Array, or ALMA. They meticulously tracked the subtle flickering in the millimeter wave light coming from the 4 lensed images of RxJ1131. The patterns of these flickers told a clear story. The light was originating from an astonishingly small region. Their calculations revealed that the black hole's corona, the source of this intense radiation, is only about 50 astronomical units across. 1 astronomical unit is the distance from the Earth to the Sun, so this means the entire super-energetic corona is roughly the size of our solar system out to its icy edges. To put that into perspective, this incredibly powerful engine, which outshines an entire galaxy of hundreds of billions of stars, is confined to a space no larger than our own cosmic backyard. It's a staggering demonstration of the efficiency of black hole physics, where immense energy is generated in a remarkably compact volume. This measurement provides the first concrete evidence supporting theories that the corona is a compact, magnetically confined structure, rather than a more extended phenomenon like a jet or a region of star formation. The discovery aligns beautifully with what we see in magnetically active stars, suggesting a universal, physical process at play. This breakthrough is profoundly important. It's not just about putting a number on the size of a corona, it's about validating our physical models of the most extreme environments in the universe. By confirming the corona's compact nature, we gain confidence in theories that propose strong magnetic fields as the driving force behind its immense energy output. This helps us refine our understanding of how black holes feed, grow, and interact with their surroundings, a process that shapes the evolution of entire galaxies. It's a crucial data point that transforms our ideas from abstract theory into observable reality, bridging the gap between mathematical models and the tangible cosmos. The story, of course, does not end here. This successful measurement of RxJ1131's corona is a powerful proof of concept, opening a new window into the hearts of quasars. Future observatories, like the Vera C. Rubin Observatory, are expected to discover thousands of new lensed quasars, providing many more targets for this micro-lensing technique. With more examples to study, we can begin to map the coronas of different black holes, comparing their sizes and structures to see how they relate to the black hole's mass or feeding rate. We are standing at the dawn of a new era in black hole astronomy, where the once invisible is slowly but surely being brought into the light.